Hi everyone, my name is Emin Serin. I'm a second-year PhD student at the Einstein Center for Neurosciences Berlin. My PhD mainly focuses on the investigation of heterogeneity in neuroimaging-based biomarkers using normative modeling and machine learning. I'm also the main developer of the NBS-Predict Toolbox, which I will introduce in this lecture. So let's start. Okay, so the objectives of today's lecture is to introduce NBS-Predict. So I'm going to first start talking about the NBS-Predict method. Then I will introduce the NBS-Predict toolbox like the graphical user interface. Then I will analyze fMRI data and visualize results using the toolbox. So let's start. As you know that the machine learning analysis has been dominant approach in fMRI analysis, including the analysis of brain networks. So what we do in the machine learning analysis is that we fit univariate model like the generalized linear model to each brain connection and then compute p-value, the corresponding p-value. However, currently we're trying to deal with very dense brain networks like those comprising more than 10,000 connections. And fitting univariate models such amount of time, unfortunately, could easily result in very famous statistical problem, which is a multiple comparisons problem. So there are several methods to control like the multiple comparisons problem, like Bonferroni correction or FDR correction, but those methods are often criticized as being too conservative. So in response to that issue, in 2010, Andrew Zalesky and colleagues developed a new method called network-based statistic. So the aim of this method is to control family-wise error rate in a weak sense by combining graph theoretical concept of connected component and the cluster-based thresholding. So although it's a very powerful method compared to the traditional correction methods like the Bonferroni or FDR, it comes with a limitation originating from the traditional statistical method. That is, it doesn't allow for making predictions at the level of individuals. So this is where NBS-Predict comes in. It's a novel connectome-based prediction method which combines the powerful features of network-based statistic and machine learning. So you can think NBS-Predict as a kind of the extension of the network-based statistic and with machine learning. So with NBS-Predict, you can not only extract effect-associated subnetworks, but also make predictions at the level of individuals using these extracted subnetworks. All right, so here you see the algorithm of the NBS-Predict. The NBS-Predict operates in a repeated nested cross-validation structure, as you see here. So starting with the input, we start analysis by providing connectivity matrix for each subject. So to be simple, we call these connectivity matrices as input data. So once we provided the input data, this input data goes into the outer loop of the cross-validation structure. So in each fold or in each iteration of cross-validation, we divide the input data into train and test set. And then using the data from the train set, we extract sparse subnetworks, which we're going to use as the feature set in machine learning analysis. This is where the original network-based statistic, where we use the original network-based statistic without permutation testing. So basically, you can think the original NBS as the feature selection algorithm in the NBS-Predict. And once we extract a sparse subnetwork, we use this subnetwork as the feature set, and we use this subnetwork to train machine learning model on the train set, and then we evaluate the performance of the trained model on the test set. So additionally, we can also optimize the hyperparameters for the corresponding machine learning algorithm in an additional inner loop, as you see here. Yeah, so we repeat those steps like k times, like for example like 5 times in the case of 5-fold cross-validation, and then we get the k different subnetworks and their associated prediction scores as outcome. So we then multiply these subnetworks with their prediction scores and then average to construct a mean matrix. So this mean matrix is all kind of a final outcome along with the overall prediction scores. So in this mean matrix, weight for each edge represents the frequency of being selected in each cross-validation structure and plus the prediction scores. And therefore, it clearly represents the contribution of each edge to the overall prediction performance. So as I said, this mean matrix is our final outcome, but still we can threshold this mean matrix to visualize subnetwork with most relevant edges. Yeah, so this is how the magic happens. All right, so NBS-Predict has several advantages over the existing methods. For example, like compared to traditional methods like GLM or NBS using GLM, the results derived from the NBS-Predict are highly generalizable. That's because it simply evaluates the auto-sample performance of the effect-associated subnetworks using cross-validation. And the second thing is that unlike generic machine learning algorithms like the logistic regression or support vector machine, the feature weights in NBS-Predict are clearly are straightforward to interpret. That's because the NBS-Predict allows you to evaluate prediction performance of the model while providing a direct mapping to the brain, so that you can easily check the relevancy of brain networks to the overall prediction performance. So that's the advantage of NBS-Predict, because the machine learning models, like the coefficients or the feature weights from the machine learning models, even from the linear ones, are very difficult to interpret because they don't say anything about the effect of interest in the data. And also, compared to the connectome-based predictive modeling, the connectome-based predictive modeling that can be only applied to the regression problems, NBS-Predict can be applied to both regression and classification problems. And finally, and importantly, it doesn't require any programming expertise because it comes with a easy-to-use graphical user interface. Okay, so the paper for the NBS-Predict is already out on NeuroImage, so you can download the paper using this link on the slides. And we also wrote a book chapter about a practical guide for applying NBS-Predict to fMRI data. The preprint version of the book chapter is already out on the OSF preprint server, so you can also download the preprint from this using this link below here. And the thing is that today we're going to also we're going to also perform one of the analyses presented in the book chapter, so it might be really beneficial to read this book chapter. Okay, so the most recent version of the Toolbox is already on the GitHub and its RC server, so you can also download the Toolbox using those links on the slides. Yeah, let's talk about today's analysis. So today we're gonna do sex classification. I picked classification instead of regression because it's a little bit more complicated, so I thought it might be more beneficial for you. But just don't worry, because like the difference is really minor. So I will also I will also quickly talk about the difference while we are setting the parameters for the analysis. What we're gonna analyze is the task-based fMRI data from the ID1000 dataset from the Amsterdam Open MRI collection. From this dataset, I discarded subjects with high head motion that left us total number of 861 subjects. The good thing with the dataset is that the data has already been pre-processed by the publishers, but still I did a few additional pre-processing steps like the motion correction, temporal filtering, and smoothing. And after pre-processing, I parcellated the brain images using Shan Atlas, which contains 268 brain regions. And then I used a Pearson correlation coefficient to construct connectivity matrix for each subject. In today's analysis, we're going to also control the confounding effect of age and total intracranial volume. You can also download the data and also the toolbox using this OSF link on the slide. All right, it's time for demo. Okay, I am now on my MATLAB window. So before running the toolbox, just to make sure that the toolbox is already added to your MATLAB path. And to do that, just right click on the toolbox and then select add to path and select the selected folders and subfolders. Okay, so we can now start the toolbox. So to do that, just write start NBS-Predict button, NBS-Predict on the command window and hit the enter button here. Okay, you will immediately presented by the welcome window of the NBS-Predict, where you can create or load workspaces for your analysis. In the current analysis, we already have a workspace, which is a dataset folder I shared with you. Just gonna let me quickly load the workspace. To do that, just click the load button here and select the OHBM6 classification file folder on my computer. Okay, so we can now start the analysis setup window by clicking the start button here. Cool. So here you see the analysis setup window of the NBS-Predict, where we're gonna set all the parameters for our analysis today. If you already have used the original NBS toolbox, it looks familiar to you because like we decided to use the similar layout, just not to confuse you with the extensively different layouts. So as you see here, there are 3 panels, which are data, models, and advanced options panels. I'm gonna go through all these panels and talk a little bit about how we can set our parameters for the data analysis. So let's start with the data panel. This panel is where we're gonna load our data and also the node descriptions. So just starting with loading our data. So the data is actually the correlation matrices. So to load the data, hit the select button here, navigate to the data folder and select commat file folder, which contains connectivity matrices for subjects. Okay, so another thing to load is a node description file. So just gonna show you how it looks like. Yeah, so the node description file should contain 4 columns. The first 3 columns should contain the X, Y, Z, M and I coordinates for the brain regions, whereas the last column should contain the node labels, like the brain regions. So in this case, like the functional networks in which the brain regions are present. For example, like the frontoparietal network or subcortical cerebellum, default mode, etc. Yeah, so this is how it looks like. And just going back to the GUI. Yeah. Again, to load the node description file, hit the select button here and navigate to the data folder and select the file starting with brain regions. Okay, so we can now continue with the models panel. So the models panel is quite important because in this panel we're going to define what kind of analysis we're going to do and also what type of machine learning model to use in our analysis. So starting with the design matrix. So as I said before that So we utilize the original NBS methods without permutation testing as feature selection algorithm in our toolbox. And that's why we need to define a design matrix. Yeah, so let me show you how it looks like. Okay, so for our analysis, the design matrix contains 4 columns. And the first 2 columns contains the 100 encoded group labels for contrasting, like for 1 for females and 0 for males. And of course, it's going to be different in the regression analysis. Like in the case of regression analysis, the first column should contain the only ones, which we also call as the intercept term, whereas the second column should contain the values for the target variable, like the IQ scores. So these 2 columns are only the difference, are the only difference between the regression and classification problems. And then the additional columns, like the third and fourth column, should contain the confound variables, like the total intracranial volume and the subject's age. Of course, it should contain more columns if you want to control more confounding variables in your analysis. Yeah, just going back to the GUI. Again, to load the design matrix, hit the select button here and select the design matrix, design sex mat here. Okay, so another important parameter to define is contrast factor. Like the contrast factor here is basically the same contrast factor like you use in your univariate analysis. So here you see the contrast factor of -1 and 1, which simply tells NBS-Predict to select the subnetwork greater in the group 2 than group 1, without controlling any confounding effect of the other variables. So to control the confound variables, just write 0 for the total intracranial volume and 0 for the subject's age. Yeah, so this is actually how our contrast vector looks like. So the thing is that we're also interested in the other case, like when NBS-Predict selects the subnetworks that are greater in the group 1 than group 2, right? That's why we're gonna define 2 sets of contrast vectors and run the analysis twice. So I strongly suggest you to run your analysis in both directions unless you have a very specific hypothesis about the direction of your analysis. Yeah, so for also the regression problems, it is a lot easier because so you don't need to run your analysis twice. So what you need to do is just only write a contrast vector like this, like a 0 for the intercept term, 1 for the target variable, and 0 for the confound variables. Let's go back to here. Okay. So the MATLAB parameter, the machine learning model parameter is very straightforward. In the NBS-Predict shows you the suitable machine learning model for your analysis for your problem based on the design matrix you provided, for our analysis, like logistic regression, support vector classification, and the other thing like the linear discriminant analysis. And also there is an option that the auto optimize option, which simply tells NBS-Predict to run the several times using the suitable machine learning models for your problem. All right, so actually from this point, we can actually run our analysis, because like we already load the correlation matrices, node descriptions, design metrics, and also we defined the critical parameters like the contrast vector and machine learning model. But in machine learning, we also define some additional parameters, especially for the model evaluation, hyperparameter optimization, and like the feature engineering. So that's why we're going to use the advanced option panel here. So the first thing we can define in this panel is the parameter for the cross-validation, which these parameters are the number of false and the number of cross-validation repetitions. So these parameters are quite important because they directly affected the granularity of the edge weights in the outcome mean matrix. So for example, like if you use higher numbers, so the edge you will end up with having like the more fine-grained edge weight distribution in your mean matrix, outcome mean matrix. But this time your analysis will definitely take longer. And so this the number of false, this parameter is also directly determined. It also depends on the sparsity of the input network, the input connectome data. For example, like if your data is really dense, I will suggest you to use higher numbers. But for our analysis, we're gonna set the K parameter to 5 and number of CV repetitions to 50. Okay, so the another important parameter to define is p-value, which is the feature selection parameter. It is also important because like it directly determines the sparsity of the subnetwork extracted in or selected in each cross-validation fault. I suggest you to use the same strategy for setting p-values like you do for your univariate analysis. For example, like if your data is really sparse, you can increase the p-value to like the higher numbers, like I don't know, 0.05 or 0.1. But in today's analysis, we're just going to use the default parameter, which is 0.01. So the another thing to define, another thing is that we can also like optimize hyperparameters. And to do that, just click here. In the current version of NBS-Predict, the hyperparameters are predefined, but you will be able to define your hyperparameters in the incoming versions. So the important criteria here is that the number of hyperparameters optimization steps. So these steps determines the dimension of the parameter space. For example, like if you set higher numbers like 10 or like 100, your parameter space will be much higher, and that could allow you the better optimization. But the drawback here is that it could take a lot of time. Like it will definitely require more computational resource. So I suggest you to consider your computational resource before setting this steps parameter. And so there are also different the searching methods, like as you see here, but we're gonna use the default searching methods, which is grid search here. Yes, so another important thing, like another parameter to define, is the permutation here. So to act permutation testing here, to just activate here, and then we actually use the permutation testing to evaluate the significance of the the model performance. And the number of permutations like 500 or 1000 are common numbers, but you can also use like if your data is really high, if your sample size is high enough, and also if you wanna do like really quick model prototyping, you can also use the lower numbers like 100, which we're gonna use today. All right, so another parameter to define is the feature scaling parameter here. So with feature scaling, the models converge faster, and hopefully they will yield a slightly higher prediction performance. And there are several options, but today we're going to use simply the standard scalar option, which is basically the z-score transformation. Okay, so there are also like additional parameters, like we can also set additional parameters like the performance metrics, as you can see here, or the seed number for the random generator, or the number of CPU cores to utilize for your analysis. Yeah, so we set all the parameters, I guess, and we can run the analysis. But we're not gonna do that because like with these parameters and also with the data with this sample size, it could easily take more than 20 hours. So that's why I also provided you the results file, so we can just skip the analysis stage, and we can just drop directly to the visualization stage. Okay, just close the window. Okay, so to run the analysis setup window, just write view NBS-Predict onto the command window here and hit the enter button. So we will ask you to load the results file, which locates under the results folder. So in this folder, there are two results files which correspond to the different two sets of contrast vectors, like the nec post for the -1 and 1 and post nec for the 1 and -1. So we're going to select the first file here. Okay, so here you see the results viewer window of the NBS-Predict. So the first thing we can do is to check the overall prediction performance. So it's located right above the figure here. So it seems like we get like the 68% of accuracy, which is comparable with sex classification performance if you control head size and age. So we can also check the permutation testing score and also the significance rate, which is significant. So by using this pop-up menu on the right-hand side, you can also check the other performance metrics. NBS-Predict automatically shows you the results from the best performing machine learning algorithm if you selected the auto optimized model option in the analysis setup window. But still, you can also check the results from the other machine learning algorithms using this pop-up menu on the right hand side here. There is also a table showing the nodal degree for brain regions in the outcome network. So the nodal degree basically means how many connections a node makes with the rest of the network. So it directly represents the kind of the importance of the brain network in a given brain region in a given network. For example, like there is a brain region from the frontoparietal network, which has a nodal degree of 150. So it means that this brain region is kind of a central hub in our outcome network, and that means it is really important in our network, and it is also important for therefore it is also important for the sex classification. Yeah, so as I said before, the main outcome of the NBS-Predict is mean matrix along with the overall prediction performance. So what we can do is we can also further threshold this mean matrix to visualize subnetwork with the most relevant edges. And to do that, just set the weight threshold on the right-hand side to 1. So it will show you the subnetwork with most relevant edges. In this subnetwork, we have 161 brain regions connected by the 425 connections. Okay, so we can also check the nodal degree for each edge in the brain network, in the subnetwork. So the good thing is that we can also evaluate the prediction performance of the threshold subnetwork, but keep in mind that the prediction performance of the subnetwork is different from the overall prediction performance, because they are basically using different sets of features. And also note that the main aim of evaluating evaluating prediction performance of subnetwork is just to get the general idea of how it performs. Please do not use it for to explore the optimal weight threshold. Otherwise, it could easily result in overfitting issues. And to evaluate the prediction performance of subnetwork, just click here, and it could take time depending on the size of the subnetwork. It basically performs 10 repeated tenfold cross validation. Okay, so you can check the performance of the subnetwork, which is around 63% of accuracy, which is good. Yeah, so what else we can do? So we can also visualize this subnetwork on a circular graph, and to do that, just click the network button here. Okay, so here you see our subnetwork on a circular graph. So as you can see here that the nodes are just numbered, but you can also visualize the labels by using this button here. And so we can also visualize a subnetwork on a 3D brain layout, and to do that, just click the BrainNet Viewer button here. It will automatically opens the BrainNet Viewer toolbox, which is a great toolbox for visualizing the brain networks. So it is simply a BrainNet Viewer toolbox. And this is our subnetwork, and we can also check the different slices here. Okay, so we can also save the brain images or brain networks using this button here. It is also possible to visualize the confusion matrix, which can be used to evaluate the prediction performance however you need. To do that, just click the confusion matrix button here. And the important thing is that these numbers are just the sum of observations across the outer false. So please don't be scared of such high numbers. I think the most important thing is just the percentage, not the numbers. Yeah, so let's just go back to the matrix here. Okay, so I think we're good to go. Oh, okay, so we can also save the figures using this save figure button here. And also for the table, just use the save table button here. All right, I think that's it for this results file. And we need to do the same thing for the other results file, but we're not going to do that because we don't have enough time for this one. But the steps are pretty much the same. I mean, it's basically the same. So that's it for the demonstration today. And yeah, so thank you so much for your attention, and please contact me via this email for further questions, and I will be happy to have you. I'm happy to help you in any way in any steps of your analysis using NBS-Predict. And thank you, and have a good day.